We're going to start talking about rational expressions now. So recall that a rational number is a fraction of integers. For example, we could have 4 over 5 or 7 over negative 2. Those are rational numbers. A rational expression is kind of like that. It is a fraction, but it's a fraction of polynomials. Okay? So, for example, we could have x plus 2 over 3x, because x plus 2 is a polynomial, and so is 3x. So if I make a fraction of the two of them, that's a rational expression. Another example that we could have 1 over x squared minus 3x minus 2. Okay? Or plus 2. Either way, again, it's a fraction made from polynomials. It's okay that this is a 1 because technically any constant is a polynomial. So for that matter, any rational number is also a rational expression because it is technically a fraction of polynomials. But we're going to focus on rational expressions that look like these, where we have a polynomial in the denominator. Okay. When we have a rational expression, we can think of it as a function. So I could say, let f of x be x plus 2 over 3x. Okay? And the reason that works is because, remember, with a function, if you give me an x, I can give you a y. Exactly one y for every x in the domain. Okay? Well, if you give me an x, we substitute in here, we calculate it, it's going to give us a number. Okay? So that's a function. Okay? This could also be a function. G of x is 1 over x squared minus 3x plus 2. Okay? So since they're functions, that means I can evaluate them. For example, I can ask, what is f of 1? In other words, what is the value of this function when I put 1 in as the value of x? Well, that's exactly what we do. We substitute that 1 in. So we'll have 1 plus 2 over 3 times 1. And then we just simplify this expression. It's 3 over 3, which reduces to 1. So f of 1 is 1 for this function f. Or I could ask, what's g of negative 2? What is the value of this function when x is negative 2? Again, same story. I put in negative 2 wherever I see an x. Okay? I do have to remember that if I have x squared, then I'm squaring whatever that value is. So negative 2 squared is going to be positive 4. So 1 over 4 plus 6 plus 2 is going to give me 1/12. Okay? What about f of 0? If I put 0 into this function for x, what happens? Well, 0 plus 2 over 3 times 0, we're going to run into a problem. 2 over 0, that's not a defined expression. So what happened? I thought if you gave me an x, I could give you a function value. Well, that's true for any x value that's in the domain of the function. The domain is the set of all allowed inputs, all allowed x values. So clearly 0 is not an allowed x value. And the reason is because it turns the denominator into 0. So anytime that we get a function with the denominator 0, whatever x value made that happen can't be in the domain. So that's how we're going to find out what the domain of a function is. Let's see how we do this. We've already seen that 0 is not in the domain of f. And the reason it was because it made the denominator 0. So what we do to actually discover that, without just randomly picking numbers and plugging them in to see if it gives us something, is we take our denominator and we set that thing equal to 0. This equation is going to be solved by precisely the value of x that makes the denominator 0, which means the value of x that we can't have in the domain of our function f. Well, this is easy to solve. Divide on both sides by 3. You get it that x is equal to 0. So that means this is the value that's excluded from the domain. So the domain of f is the set of all x values such that x is not equal to 0. Or you could write this another way. The interval from negative infinity to 0 union with the interval from 0 to infinity. Both these notations mean the same thing. It means every real number except for 0 gets left out. Okay? Now, let's look at another function and find its domain. We'll look at g of x in a minute, but first, let's look at a third function. H of x is going to be x minus 1 over 2x plus 5. All right. It's a rational function because x minus 1 is a polynomial, 2x plus 5 is a polynomial, and I'm taking the fraction of them. So, what is the domain? The domain of h is, well, I have to figure out what is going to get left out here. And what's going to get left out is whatever makes that denominator 0. So I set 2x plus 5 equal to 0 and solve. So 2x equals negative 5. X is going to be negative 2.5. This value will be left out, so the domain is the set of all x values such that x is not equal to that negative 2.5. Again, we can write that in interval notation as the interval from negative infinity to negative 2.5 union negative 2.5 to infinity. Negative 2.5 is left out. Okay, so far so good. But now let's see what happens when we try to find the domain of g. Again, it's going to be any x values that make our denominator 0. So x squared minus 3x plus 2 equals 0 will give us the offending numbers. But the difference between f and h and g is that now this is a quadratic equation. We can't solve it by the linear methods we used here. We need to solve this by factoring. Okay? So we need a couple numbers whose product is 2 that add up to negative 3. That's going to be negative 1 and negative 2. Okay? So now that we've factored this, set each factor equal to 0 because either one or the other of these has to be 0 to make the product equal to 0. So either x minus 1 equals 0 or x minus 2 equals 0. And so solving the first one, we get x equals 1. Or solving the second one, we get that x equals 2. So for the function g of x, both 1 and 2 have to be left out of the domain. Neither one of them will give me a value for this function. You can check it yourself. If you substitute a 1 or a 2 in for the x, both will give you denominator 0. And so, our domain is the set of x values such that x is not equal to 1 and also not equal to 2. In interval notation, this is the interval from negative infinity to 1, together with the interval from 1 to 2, together with the interval from 2 to infinity. Since I'm leaving out 2 points, that's going to break my real number line up into 3 intervals.